Hello everyone. So today I came with the next discussion, that is along with our previous discussion over functionalization of graphene. So if you recall our previous recorded lecture where we have talked about how covalently any molecule atoms can be attached to a graphene, right? And then if it is a covalent bonded, then the functionalization will result in the change of hybridization. The sp2 hybrid graphene will convert into sp3 hybrid system. So that is the covalent, and you have already seen, like in case of graphene, how it is going to be happen. Similarly, in case of graphene oxide, right? Now, in the same direction, if you remember this picture, let me open the. I think if you see my cursor, you see the point 2 and point 3. So there is possibility that the pi electron of graphene can also interact with other atoms, molecules or ions without having any change in hybridization or covalent bonding. So there's two possibility, as you see, like it may form a complex, you can say the complexation. So here it can be considered like graphene as electron donating pi ligand. So this is the one, or maybe you can say graphene can also work as a electron acceptor, and then we can consider it could be the charge transfer absorption, right? And then how it can basically have interaction with some defective graphene like monovalent, and or maybe some curved graphene. So these are other point, or these are other possibilities through which graphene can interact with other molecules, atoms or ions. Right. So in the same timeline, today we will discuss what are the possibility about non-covalent bonding. So non-covalent bonding, what do we mean by non-covalent bonding? Means some other force of attraction or interaction is there between graphene and that particular molecule. So it could be van der Waals interaction, or maybe electrostatic, or maybe the induction based interaction could be there. So these different possibilities are there. So let's see what are these. So the non-covalent functionalization of graphene means van der Waals interaction, or maybe the ionic interaction. And if we say it offers the possibility of attaching functional group to graphene without disturbing the electronic network. So we can say this is a kind of non-covalent bonding, and here mainly pi interaction is going to play an important role. So one example could be graphene is going to attach with the ligand via non-covalent interaction. So what do we mean by the ligand? The ligand is an ion or a molecule that has a center atom. It's maybe metal. It's a metal ligand, and then form a complex. So how this ligand can be interacted with graphene? So as we know, graphene is a pi system. Pi system means there is a pi, pz electron is free to interact, and non-covalent intermolecular interaction involve basically pi systems. And if there is a pi system, then graphene is able to interact with different kind of molecular complexes. So these ligands or complexes could be protein, could be enzymes, drug complex, DNA, protein complex, organic supermolecules, or maybe the functional nanomaterials. This material could be anything. and if that complex is going to interact with the graphene, so it will be interacted through a pi system or pi electron. So this interaction can be divided into various type. So how your pi is going to interact, or what is the interacting molecule, based on that we can just divide it. It either may be a non-polar gas, let's say argon is there, that is going to interact with the pi electron of graphene. So it may form some interaction with graphene and non-polar molecule. So it's a non-polar gas and pi interaction. Maybe the hydrogen is interacting with the pi molecule, so hydrogen and pi interaction is there. Similarly, if other material which is also having similar feature as graphene, means one electron which is behaving like a pi electron, so it's maybe pi interaction. Or if we are having a cation, so cation, then your electron is negative, so it may have some kind of electrostatic interaction. And the other, that is the fifth one, it is little bit surprising, but it is also observed in case of graphene, like anion and pi interaction. It means the negative ions and pi interaction is also possible. So we can see little bit here the detail. So non-polar gas and pi interaction is when a counter molecules, means the molecule which is going to attach with graphene is either a rare gas atom or a non-polar molecule, such as gas, dimers, hydrocarbons. If they are going to attach, so what is the module of attachment or interaction? So basically there is a dispersion energy which is playing a important role. And dispersion energy in general sense we can say, like for short period of time, if there is a kind of dipole formation, and if that kind of dipole formation is going to convert into an interaction with pi system of the graphene, then we may say this is a kind of dispersion energy dominated interaction, which is not possible in case of any polar molecule or any Lewis acid. In that case, it could be an electrostatic interaction, and maybe dispersion energies interaction is also possible. So here you can see one example. Let's say fluorine is interacting with the benzene and benzene argon complex. So here you can see the argon is having an attachment with the fluoro substituted benzene. So benzene you can consider, it's not exactly the example of graphene, but we can understand the similar like graphene. There is a BZ electrons, and then argon can have an interaction that is non-polar gas pi interaction, and you just can refer this research article to get a little bit more detail about non-polar gas and pi interaction. Similarly, the hydrogen and pi interaction. So in this case, one of the hydrogen bond is going to interact with hydrogen. Maybe the ligand could be anything, right? So the bonding will be through hydrogen, right? The system may be the complex. So I'm not saying only hydrogen is going to interact. Maybe there is ammonia, NH3, or maybe some other molecule which is one end is hydrogen, and if that hydrogen is bonding with the your pi molecule, then we can say there is a hydrogen and pi interaction, right? So the polarizability of pi electron system play a key role in governing the nature and geometry of hydrogen pi interaction, and the magnitude of dispersion energy tend to be proportional to the number of electrons participated in the interaction. So basically, how many number of electrons are there in the interaction, that will govern the dispersion energy, whether it's high or low. Similarly, pi-pi interaction. So in pi-pi interaction is basically the interaction between similar kind of systems. So let's say in the both the system, pi system is negatively charged, diffuse electron cloud of pi system. So exhibit an attractive interaction sometime. So when both pi system has similar electron density, interaction is again predominated by the dispersion interaction, because the system is same, both are having their negative electrons. So the dispersion interaction will be there to have an interaction between pi and pi electrons. So when one of the system is electron rich and other electron deficient, the resulting complex are bound by the induction interaction. But if this is the case, see, the first is the case is when the systems are similar, both are having a large number of electron, which is negative the charge, having same electron cloud, then it will be a dispersion interaction. Otherwise, if one is the deficient and one is the rich, so of course there is going to be an induction interaction, and then they will be bounded to each other. So the pi-pi interaction is one of the most important driving force for the supermolecular self-assembly. Next one is cation and pi interaction. So this is obvious, simple, we can easily understand it, because our counter molecule is a metal cation which is having a positive charge, and then our pi is interaction is having an extra electron, so it is negatively charged. So there could be there will be a electrostatic interaction and sometimes also induction energy. Both can dominate in cation and pi interaction. So positively charged cation with negatively charged pi electron form a cloud. An accurate estimate of the interaction energies require the inclusion of polarizability of the pi system. Here you can see the example. It may form a complex with sodium, copper or silver ions. Favor the conformation of cation above the pi centroid. So means just at the center of the ring it may attach if we are having sodium, copper, silver kind of complex, and if we having other, let's say the gold, PD, PT or Hg kind of complexes to attach with the pi, then it will be off-centered. So it will not be the center of the point, it will be off-centered, and pi quadrant will be the pi centroid. Maybe you can see this image. So here sodium is here, if sodium is attached at the center of the. The next one is anion and pi interaction. That is little bit surprising because your pi system is negative and anion is also negative. So in both the cases there could be a repulsive interaction, but still here if the system is quite large, then the total interaction energy may depend upon electrostatic and induction energies. And however, as you have seen in the first case, dispersion energy could be again quite high in that case, and it may form an anion pi complex. So though electrostatically it is not favorable, however dispersion energy may play an important role and anion and pi complex may form, and the total interaction energy of anion and pi complex is almost equivalent to the energy which is we can observe in case of cation pi complex. So we cannot say this is also very weak, it's also a little bit strong complex, but this is not true in all cases. It depends in when the dispersion energy is relatively high, that time only we are able to see the anion and pi interaction. Here we can see the one example, even same thing is written, unexpectedly strong anion P interaction on graphene flags. You read this journal of computational chemistry published in 12. So here you have studied basically how these halide ions, fluorine, chlorine, bromine, on the hydrogenated graphene flags using the density functional theory. And here you can see within this carbon network of graphene, you can see how this one atom, if you are able to see here, if you are able to see here how this graphene atom is this fluorine atom is attached, here bromine, and here, sorry, here's chlorine atoms. See this top color. So the location, the position between these two bonds, it could be different, but there is a possibility to attach this kind of atom in between. So if you are interested, you can just follow this research article to get the more detail. So the unexpectedly large absorption energy ascribed to the effective donor-acceptor interaction between the halide anion and the graphene flags. Now the next topic is, let's say we having some nanomaterials. So how it can be attached or functionalized on graphene. So nanoparticle functionalization of graphene and graphene oxide. So as you know, graphene is a monolayer. It has very large active surface area to interact with any molecule. So that is also going to be advantageous when we are targeting to functionalize graphene with any nanomaterials or nanoparticles. So in this case, if you see here, okay, a variety of different material. It could be metal, it could be metal oxide, even some mix, or maybe the alloy metal oxide, or sorry, metals, or any other mixed material can be attached in graphene, and the target could be. See, we are already familiar with the very specific properties of graphene, but the other material has their own properties, and if we make the functionalization of graphene with these materials, may we can tune the property, we can redesign the material as per the applications, and the material properties will be greatly tunable. So that kind of advantage is possible if we are targeting to functionalize the graphene with nanoparticle or nanomaterials. So if we see what kind of material is there, so of course we can deposit with different kind of metal nanoparticles, or maybe the metal oxide nanoparticles, quantum dots, other nanoparticles which not belong to this category, or something else we can say. So I'm just going to show couple of examples only, and that will give a generic idea. If you are interested, I already share that review articles and some more reading references. So you just read it, and if you have any doubt or any queries, we may interact and have a discussion. So here it will just a kind of generic information I'm going to talk. So precious metal means what? If we can discuss the metal nanoparticle on graphene, of course, these materials is having very good catalytic, magnetic and other properties. So which can be also carry forwarded here with the graphene, and we can get a new class of material. So the noble material could be platinum, gold, silver, rhenium, PD, or maybe the alloy of these materials. So a lot of research available in this area, and here we can see one example how we can functionalize gold nanoparticle over graphene oxide. So it's a chemical method. The method is very simple. After growth of or synthesis of graphene oxide, we can just do the reduction of gold ion. So the reduction process, you just take the solution of gold chloride and just reduce in the presence of NaBH4 and the graphene suspension. We will going to get the nicely decorated gold nanoparticle over graphene oxide. And here you can see, so here they just compared two different idea. If you see the picture A here and picture B, so A shows just there is a variation in the process. They said if you will prepare the graphene oxide first, and then you use the dispersion of graphene oxide and you will reduce the gold, you will get the attachment, but maybe the particle size could be different, and also the density of gold nanoparticle will be different as compared to the second process. So in B, this is just a TM image just to show like these black dot spots are the gold particles, okay, and this is the sheet of graphene. Similarly here, this is the sheet of graphene. Here you can see the density of gold particle is higher, and also the diameter, you can see the shape of the gold particle is though not very uniform, but at least size is look like not so much varying. So this is the second, when during the exfoliation of graphene oxide, they are doing the gold nanoparticle reduction. So they are calling the in situ. Okay. So this is the one way to demonstrate like how gold nanoparticle can be decorated over a graphene oxide. See the other example. Here they have developed a memory device in which they have studied the effect of gold functionalization over the performance of memory device. You just get the reference. It is 320 reference, and this paper is published in Wiley. So you just go through this reference. Here they have just demonstrated, like if they make a device in which silicon oxide, and then graphene oxide is dispersed here in the figure B, and they having some kind of photoresist to then how they develop the electrode over the graphene oxide. Then they reduce the graphene oxide, because the graphene oxide and reduced graphene oxide has different properties. And then the third option is, even when they can coat the gold nanoparticle over the reduced graphene oxide. And then of course the top gate electrode. So this is the device performance. So maybe we can study the effect of gold. So without coating gold and after coating gold, how this memory device will behave. That kind of analysis they have investigated here in this research article. But this is possible, like if we are adding the gold nanoparticle, we are going to achieve the different functionality of graphene oxide. This is another example where platinum has been decorated over reduced graphene oxide. So again the system is same. You are saying, see, this is the graphite, then they did the oxidation process. You already are aware about the oxidation process. So fabricate the graphene oxide, and then this day here in the third step they are showing, like after reduction of platinum, like chemical approach, they can get the attachment of particles, platinum particle over the sheet, and this is just a verification by TM analysis. This particle is, see the side image, this shows like it's crystalline platinum particle, and which is attached over the graphene sheet, which you can see here entire TM image. Another example is there whether reduced graphene oxide is decorated with PD, and the B is the when it is decorated with copper, and the C is when it is decorated with copper and PD nanoparticles. Next detail is already given here. I am just giving the example, like these kind of possibilities are there. Similarly, here they have investigated even how the plasmonic property of graphene or decorated graphene is going to be changed when we are decorating different kind of material. So see this gold, this is the visual absorption spectra, how this decoration of gold, silver and copper is going to give us different absorption peak. And here they have just shown like how these metal particles are attached in case in graphene of oxide or reduced graphene oxide. Other may be the metal oxide. So again, variety of metal oxide, it could be tin oxide, titanium oxide, zinc oxide, magnesium oxide, cobalt oxide. All of these are reported. A lot of reports are there. And here again, since this oxide is very much useful for catalytic applications, for sensing applications, similarly energy storage, TCO, flexible electronics, photovoltaics. So if we can modify it graphene with these kind of particles, we are going to create a new class of material or a new hybrid material which is going to give a very different properties and can be, and graphene and functionalized graphene with these kind of nanoparticle can be used in these variety of applications. So that was the target. So here one example we can see, like when the reduced graphene oxide is modified or functionalized with tin oxide nanoparticles. So in this study, whatever I'm discussing here, they have shown like if only tin oxide is used as an electrode material for lithium ion batteries, this is not so good. There are some issues. The issues is like during charging, discharging, this material usually breaks or the cracks appears at the anode. And if cracks is there, then it is going to reduce the life of battery. So once they add the reduced graphene oxide, okay, between the tin oxide nanoparticles. So basically your system is overall tin oxide nanoparticle. Just in between they are just adding some amount of reduced graphene oxide, and they observe that this problem is solve in the large extent. Here this is the example, like the pore and wide space that form in case protect the anode from cracking, minimizing the expansion of SNO2. So see see this black color. These are the graphene reduced graphene oxide sites, and this is SNO2. So whenever there is a pore or any other area is there, this graphene nano ribbons is going to fill that area. And they have investigated the charge and discharge cycle as well as durability of this battery electrode, and they found that this is reasonably good solution to resolve that kind of issue. Next is, we can say the RGO is modified with cobalt oxide. So again the idea is same. We have graphene, we have the cobalt ion. If you just reduce the cobalt ion, we can get the cobalt hydride modified graphene composite, and then if you just do a heat treatment, then we can convert this hydride into the oxide, and then graphene composite will be formed. So this is another example. Similarly, RGO with TiO2. So this is one, like complexation, nucleation and condensation. So based on this reaction, if you just have a sheet of graphene and then your TiO2 precursor, and if you do the nucleation and condensation, then we are going to get the rutile and anatase TiO2. So based on the different condition, even the type of TiO2 will be also different, and that is going to attach over the graphene sheet. Other is RgO-TiO2, again here, which has shown the TiO2 modified graphene, and they have demonstrated like when we are exciting this material with the UV light, the hydrogen production amount is higher when we are having a mixed material. Third, even here they have shown like what the change in the color happened. Let's say TiO2 is almost milkish or this whitish in the color. When we are having TiO2 GO, it's brownish in color. Once you are reducing this, then suspension become TiO2 and reduced graphene oxide. So slightly blackish in the color. And here you can see the clear cut difference in the absorption peak. Other is like when we can attach two different systems. So earlier you have seen only TiO2 or metal oxide. There is possibility where you can attach metal oxide as well as metal. So this is one example where RGO is reduced graphene oxide is functionalized with TiO2 and Ag. And here they have demonstrated how this light is going to interact with this three material based system, and what kind of difference will be there if you are just studying, let's say, the photoactivity. And even here they have shown in the bottom, like when they are exciting with HNU, then adding with the GO, the color will be different, and then silver, the color is different, and when the silver is formed and the TiO2, RgO and Ag, then the color is different. Means the different color means the interaction with the light is different in all three materials. Other possibility is we may have the quantum dot of different group third or fifth and group second and sixth element. And one example is, let's say we have the CDSE quantum dot, which is functionalized with the graphene oxide. So you already know if we are going to have a variation in the size of the CDSE, there will be different in the color of the particles. If you just illuminate with the UV light, then we are going to see the different color. That basically give us the idea about the quantum confinement. So that property will be retained again if we are going to modify the graphene oxide with CDSE particles, and they have shown very good data here, like the 6 minute to 6 minute to 60-minute functionalization, so which basically give the difference in the size, and once the difference in the size will be there, then we can see the difference in the color. So this is the suspension of GO and CDSE functionalized particles. Other is, we may have another material, let's say silicon particles or the tin particle or the cobalt hydroxide. And here is the one example where they have made the composite material of graphene oxide with silicon nanoparticle, and then they have fabricated the paper of graphene oxide silicon composite material, and this color is little bit brownish, and this shows when they have reduced the material. So we have the reduced graphene oxide with silicon, then we are going to have the blackish in the color, which shows like it's a reduced graphene oxide. So these were the basically the idea is how we can attach any extra atom or a molecule or ion. The third is we may have the doping also. See, rather than just having an interaction with the graphene, either it's covalent or non-covalent, there is also possibility just to replace some atom, or if there is any vacancy, then just fill that vacancy with some atom. So, modification by substitutional doping is also possible. So carbon atom from the hexagonal honeycomb lattice of graphene can be substituted by nitrogen or boron or some other atom also. We have to just see the feasibility and what are the basic criteria to have that kind of substitution. So if we are doping with this, we either create N type of behavior or P type of behavior. So as you know, if it's a pure graphene, it's not having N or P type, right? But by just this kind of doping, we can create either N and P type material. And if we are attaching a N-type, basically this nitrogen, then we are going to create N-type graphene and it will be electron-rich system. And this N-type dope graphene, basically nitrogen dope graphene, is extensively studied. There are a number of reports you can see, and it shows like N-dope graphene sheet are formed by the substitution of oxygen or carbon atoms with nitrogen. So if there is a pure graphene, then carbon, and if it's a graphene oxide, then of course oxygen will be replaced. And it can be achieved just during reduction or annealing in situ during the growth of graphene in the CVD process. You can just supply some amount of nitrogen or by arc discharge or salvothermal method. So variety of different technique can be utilized to achieve the nitrogen doping. Oxygen or sp3 carbon atom that are situated at the defect site of GO can be substituted by nitrogen. Okay. So here even one report is there in which the nitrogen dope graphene based fit has been demonstrated, and this graphene doping is achieved just by heating the graphene in ammonia gas. And they said that the existence of CN bond identified by XPS and nanometer scale secondary and mass spectroscopy. And also they have observed like most of the CN bond is appear. This is a kind of ribbon, so edge is more destructive or more defective, so this is more dominating for this kind of interaction. So most of the interaction is happening at the edge of this, and then they have investigated how the property is going to be changed of a feed once it is modified with nitrogen. So I would stop here today. So today we discuss at least the three things. The first one was how we can have the interaction of graphene with other molecules which is non-covalent. Means there is no change in the electronic system. The electronic system will be same. Just we are having some interaction through pi electron, right? The second was if we have some nanomaterials. It could be metals, metal oxide, or maybe the mix of these two. How they can be attached to a graphene, and then how the property is going to be changed. And the third option is we can also think for the substitutional doping of graphene just to change the properties. So here I have at least covered the more generic aspect of surface functionalization of graphene, and these two three discussion, this topic is already covered. Now we'll meet with the next topic, and that we will think what could be there, whether the other 2D materials or the application of graphene. So till time, thank you very much. Thank you.